Hello all. In this video we are going to discuss the compound microscope. Before we start the topic of compound microscope, we first discuss its predecessor, the magnifier, which is a simple microscope. It consists of a single lens. The image formation by magnifier can be understood clearly from this ray diagram. This is a converging lens, optical axis, principal axis, focal point and the focal length f of converging lens, an object that lies just within the focal point at a distance of u from the center of the lens. We draw two light rays from the top of an object. They refract on passing through the converging lens. When we view from this position, these light rays appear to enter our eye or appear to come from a point that is beyond the actual object. If the rays are extended backward, we see that the light rays appear to emanate from a point beyond the object and it is higher up from the top of the actual object. So, the light rays which actually emanated from the top of the object, upon refraction through the lens and entering our eyes, they appear to be coming from this point, which is higher up than the actual top of the object. So we can clearly see that we see a magnified image of an object when the light rays are refracted through the lens. So it is due to the refraction of light rays that we see the top of object which is higher up than the top of actual object, and hence we obtain a magnified image of an object. So the tiny object can be seen enlarged in size, magnified in size by the use of converging lens as such. In this first diagram, we have shown an object closest to our eye so that it can be seen clearly without having to strain our eyes, without blurred view. So at this distance, if the object is brought closer than this distance, then object will look blurred, it will not look clear. We will have to strain our eyes in order to see it clearly. So this is the minimum distance from our eye where an object can be seen bigger in size and clear. The angle that an object subtend to our eye at this distance, this is the maximum angle that is subtended at our eye where we have a clear vision of an object. In order to view this object even bigger, we might consider bringing this object even closer to our eye, but it will not work, as we know that when an object is brought closer and closer to our eye, it appears bigger and bigger in size. But this idea will not work here. If we bring this object even closer to our eye, it will start looking blurred. So in order to view this object in magnified image, we can use a converging lens. Place it before our eyes, and then through this lens we can view an object. An object will appear bigger in size, as already have outlined in this ray diagram. However, there is a limitation of using a single converging lens in magnification of an object. How large magnification can be achieved? There is a limitation with a single lens. To further magnify an image, we might consider using another converging lens. We use two converging lenses, and the effect of magnification due to the two converging lenses is compounded, and even larger magnification can be achieved. The magnification effect of two converging lenses combines and produce even higher magnification. So this compounding of the effect of magnification by the two lenses, this gives rise to a name compound microscope to the device consisting of two converging lenses. Let's see how using two converging lenses can achieve even higher magnification. Before we go ahead, let's note that the maximum magnification that can be achieved with a single converging lens is about 20. Further magnification can be achieved by using more lenses. We now use two lenses and see how the magnification can be increased. There are two converging lenses. One lens is called objective. It has a focal length f, which is the focal length is very small, just few centimeters. The focal point is f0. This lens directly faces object and light rays from the object enter in our device through this first lens. This lens is known as objective. Another lens through which we view is called eyepiece. It has a focal length denoted by Fe, focal point F, and the focal point is capital Fe. This grey color line represents common principal axis of two lenses. An object O is placed little beyond the focal point. Now an object is beyond the focal point because the image of this object will be formed on the other side of the lens. In case of magnifier, the object was lying within the focal length. This is the ray diagram showing magnification of an object by a single converging lens, the magnifier. The object is within the focal length from the lens. When object is within the focal length, the image is formed on the same side as where the object is present. The image is upright and magnified. But in the present case, the object will be placed little beyond the focal point and the image will be formed on the other side of the lens. Here we see the object is little beyond the focal point. Again we draw two light rays from top of an arrow and see where the image of the top of an arrow is formed. Here we see that the light rays from the top of an arrow, after refraction through the objective lens, they meet together here. So it is at this point the real image of the top of an arrow is formed. While it is easy to show that the image of the bottom of an object is formed on the same line, the principal axis, and hence it can be understood that the image point of this object produces inverted image of an object, means the highest point appear lowest below the principal axis, while the bottom of an object is present on the principal axis itself, and we get an inverted image of an object. This is an inverted and real image, and it is also somewhat magnified. So some magnification is already achieved with an objective. Further magnification is achieved by an eyepiece. Now this image I1 act as an object for an eyepiece, and the magnification of this image I1 takes place in just the same way as the magnifier. Let's see how it happens. Finally, we view from this position. The light rays are entering in our eye from a direction different from the direction in which they were actually emitted from the top of an object. If we produce these light rays backward, they meet at this point. The point in which these light rays meet represent the point where the image of the top of an object is seen. So the image of a top of an object is eventually seen at this point, which is further below than the top of this image. So here we see that the image formed by an objective is further magnified. This image acts as an object for eyepiece, and then this eyepiece, after the light rays refract through this eyepiece and produce an and inverted image of this object here. We now discuss magnification quantitatively. In this figure, we have shown second focal point for an objective. First focal point for an objective is not shown for the present analysis. The distance between the focal points of objective and eyepiece is called tube length. L is a tube length. First we find magnification produced by an objective, the linear magnification. MO. We know that the linear magnification is defined as the ratio of image size, which is H2, this is H2 image size, and the object size. So object size is HO and the image size is HI in the present case. The image size is denoted by HI. To calculate linear magnification produced by an objective, we will have to measure the height of image and height of object. Basically, the microscope is used to view very small objects, and it will be difficult to measure the size of an object. Also, it is difficult to measure the size of an image. It is comparatively easier to measure the parameters that are involved in this ray diagram. There are certain parameters in the ray diagram that can be easily measured in experiments. So we try to relate this formula with the parameters appearing in this ray diagram. To do so, we will have to do some construction. We now draw these triangles. Look at the triangles. These triangles gives us clues about how we can transform this formula for linear magnification into the one that involve parameters in this ray diagram. We redraw these triangles in magnified view. This is one triangle, let's name it PQR, and another triangle ABC. Note that the angles alpha in both the triangles are equal. In triangle PQR, we can write tan alpha equal to the opposite side QR by the adjacent side. Adjacent side is PQ. Now QR, we know that the image size is negative when it is inverted according to sign convention. So image size H dash is negative QR, and we can therefore write it the PQ. PQ represents the distance between two focal points, the tube length. So PQ is equal to L. We substitute for them, we replace QR by negative H dash and PQ by L. This is tan alpha for a triangle PQR. Now, in triangle ABC, we similarly have tan alpha equal to the ratio of the opposite side AB and the adjacent side BC. AB represents object size, and object size is positive because object is erect upward above the principal axis. So AB is equal to object size, while BC is the focal length of an objective. Substituting for them gives us tan alpha equal to HO upon FO. Now this is tan alpha and this is also tan alpha. So we equate negative H dash by L. I write here negative H dash by L is equated with HO upon FO. This gives us negative H dash upon HO equal L upon FO. One mistake made here. For a linear magnification produced by an objective, the image size referred to H dash because this is the image produced by an objective. So we have to write H dash here. We delete HI. From this equation, we obtain H dash upon HO equal to negative L upon FO. And H dash upon HO is just the linear magnification produced by an objective. So we have linear magnification produced by an objective equal to negative L upon FO. we obtain linear magnification produced by an objective MO as negative L upon F0. This is just the first part of the magnification. The image produced by an objective is further magnified by an eyepiece. Now we wish to calculate magnification by an eyepiece, but as has been already pointed out, eyepiece simply act as a magnifier. So formulas we derived for magnifier, formulas of angular magnification, the same formulas apply in case of eyepiece also, because it simply act as a magnifier. And we know that when the image formed by a magnifier, that is by an eyepiece in this case, when the image is at a near point, the magnification is given by 1 plus d upon Fe. Fe represent the focal length of eyepiece and Me is the magnification produced by an eyepiece when the image is at a near point. However, it is always comfortable to view image form at an infinity. So we often talk about magnification when an image is formed at an infinity. When image is formed at an infinity, the magnification is d by Fe. So here we have two magnifications in a row. The first magnification produced by an objective and second magnification produced by an eyepiece. These two magnifications combine together to produce a total magnification of two converging lines together, achieved by two converging lines, which is the compound microscope. So total magnification is the combined effect of these two magnification. Mathematically, the total magnification is the product of these two magnification, one by objective and other by an eyepiece. So total magnification is the product of objective magnification and eyepiece magnification, which finally gives us the formula for magnification by a compound microscope, negative LD upon FO FE. Thank you.